Hello everybody and welcome back to another video on my channel. Today we will be talking about one very important technique in integration known as partial fractions. So without further ado, let's move on to the video. So this is really what partial fractions is about. Let's say we have an integral of x or over x plus 1 times x plus 2 dx. Now, normally if it was something like x plus 2 times x plus 1 over x dx, that would be more manageable since we could split it apart in 2x over x plus 1. Sorry, x plus 2 over x times x plus 1. And we could work something out from there. But in this, we don't have that choice. So instead of having it as one fraction, what if we make it two fractions? So what we could do is we could say x over x plus 1 times x plus 2 is equal to some number a over x plus 1 plus some number b over x plus 1. Then it would be sort of like solving a system of equations. And that is very, very easy to do. And that could also give us easy integrals to solve over there. So that's the gist of partial fraction decomposition, or the method of partial fractions. So let's go on to what different types of partial fraction decomposition there are there, and then we can move on to an example. Alright, so there are four main. Method number one, which is very similar to what we have here. You have the integral of p of x over ax plus b cx plus d dx. This becomes a, capital A, over ax plus b plus capital B over cx plus d is equal to p of x over ax plus b times cx plus d. And that's method one. Very simple, exactly what we did. But what if instead of these being distinct factors, what if they were the same? What if we had p of x over ax plus b squared dx? And just so you know, this method will apply to any power, but I'm just going to show you for squared. Well, this would mean this, or at least the fraction, this fraction would equal a over ax plus b, capital A, plus b over ax plus b squared, and you would add powers to go so on and so on and so on. Now, we've just covered linear factors. What about quadratic factor? Now, let's say we can't factor a quadratic factor, which is okay. Very few quadratics out of all the quadratics can actually be factored. So we have ax squared plus bx plus c. Well, this is equal to, this is going to be ax plus b over the whole quadratic. And the reason it's ax plus b is if you look at all of this, except for this is slightly different. This non-reducible, this like repeated is different. But if you look for the case where it's not repeated, you see degree 0, degree 1, degree 0, degree 1. So there's always a degree difference of 1 between the numerator and denominator. And we're doing the same thing for this. Degree 1, degree 2. So those are three of the four methods. We've covered distinct quadratic, distinct linear, repeated linear. Now, what about repeated quadratic? And turns out we have something for this also. So p of x dx over ax squared plus bx plus c. And let's square that. Well, this gets us ax plus b over ax squared plus bx plus c plus a1x plus b1 over ax squared plus bx plus c squared. This continues on and on and on until the factors are done. So that's all Delhi. These are all the types. And I've even showed you how to solve it, where you basically remove it and you multiply both sides by the factor, and it turns into a system of equations similar to what we did in just algebra with the system of equations, or with use substitution and trig substitution. So now it's time I walk you through an example. For this video, I will have one example to demonstrate the problem-solving method, as the same thing can pretty much be applied to every single one of these, as long as you remember these four methods over here and which one of the four methods you have to use. Here is our example. Solve the integral of 1 over x plus 3 multiplied by 2x plus 1 dx. So, as I said earlier, this video is about partial fractions. So, let's use our partial fractions method. Now, you realize this aligns with method 1, as there are two distinct linear factors. So, this will be 1 over x plus 3, 2x plus 1 is equal to a over x plus 3 plus b over 2x plus 1. Why not? So, let's multiply this out. We get a multiplied by 2x plus 1 plus b multiplied by x plus 3 is equal to 1. And continuing to solve that, we get 2ax plus a plus bx plus 3b is equal to 1. And factoring the x's together, we get x multiplied by 2a plus b, and then factoring the 1's, we just get a plus 3b. And this is equal to 0x plus 1. And notice how I added the 0x over here. This 0x corresponds to this term, and this a plus 3b corresponds to this term. So, we get a plus 3b is equal to 1, and 2a plus b is equal to 0. So, we have a is equal to negative b over 2. Plugging that in gets negative b over 2 plus 3b is equal to 1. So that means 5 by 2b is equal to 1, and b is equal to 2 by 5, and a is equal to negative 1 by 5. From there, all we have to do is just plug it in. So we get negative 1 by 5 multiplied by the integral of 1 over x plus 3 dx, plus then 2 over 5 multiplied the integral of 2x plus 1 dx, and then with u substitution, we get this 1 by 5, then this becomes u plus 1, and this just natural logarithm. So we get minus ln x plus 3 over 5 plus natural logarithm of 2x plus 1 over 5 plus c, and that is our final answer to this problem. And I hope you learned something new today. This is not a very complicated topic, but it is extremely useful for simplifying things that would normally be extremely weird and difficult to simplify. So, thank you so much. See you in the next one, and bye-bye.